There's a size where big stops meaning anything, where numbers stop helping, where comparison fails. Neil deGrasse Tyson says the largest galaxy, we've discovered lives beyond that line. It's not just larger than the Milky Way, it's larger than what our instincts say should be possible. And the unsettling part isn't its size. It's the realization that the universe didn't need to stay within limits we could understand. Welcome to Simulation Hypothesis. This is a place for people who feel that the universe is far stranger than we're usually told. We don't chase headlines here. We slow down, question scale, question certainty, and follow what the science actually implies when you stop turning it into sound bites. If you're new, stay with us, because what we're about to unpack only gets more uncomfortable the further it goes. When astronomers announced the discovery of one of the largest galaxies ever observed, most people reacted the same way they always do. Bigger than the Milky Way, bigger than Andromeda, bigger than anything we've seen before. The mind tries to file it away by comparison, as if scale works like a leaderboard. But as Neil deGrasse Tyson often reminds people, comparison is a psychological crutch. It helps us feel oriented in a universe that doesn't actually care whether we feel oriented at all. Because once you pass a certain size, big stops being a meaningful word. The Milky Way is about 100,000 light-years across. That already stretches the imagination. Light itself, the fastest thing that exists, takes 100,000 years to cross it. And yet the galaxy at the center of this discussion stretches not by thousands, not by hundreds of thousands, but by millions of light-years. Its radio structures alone extend so far that entire galaxies could sit inside them without ever noticing they were enclosed. At that point, you are no longer talking about a galaxy the way most people understand the term. You are talking about something that occupies space on a scale where cause and effect become strangely detached. Light leaving one edge of this structure will not reach the other edge until long after civilizations have risen and vanished somewhere else in the universe. Whatever created this thing began its work when Earth itself was still geologically young, and it has continued quietly, uninterrupted, while stars were born and died around it. And here's the unsettling part. The universe is not supposed to allow this. According to our best models of how galaxies form and evolve, growth is meant to be regulated. Gravity pulls matter together, yes, but feedback pushes back. Black holes heat surrounding gas. Star formation consumes fuel. Cosmic expansion stretches everything apart. Over time, balance is supposed to emerge. Galaxies are meant to settle into sizes that make statistical sense within the cosmic web. This one didn't. Its central black hole launched jets of energy that stayed coherent for distances so extreme that they crossed multiple environments that should have disrupted them. Turbulence, collisions, magnetic instabilities, all the things that normally tear structures apart over time, somehow failed to do their job. Instead, those jets carved colossal lobes through intergalactic space, leaving behind structures so vast that they blur the boundary between a galaxy and the universe itself. Ironically, the black hole is not the mystery here. We understand how black holes accrete matter. We understand how magnetic fields twist and accelerate plasma. What we don't understand is endurance at this scale. How something can remain organized, directional, and stable across millions of light years while the universe expands beneath it. This is the point Neil deGrasse Tyson tends to lean into discomfort rather than reassurance. Because when structures exist far beyond what intuition allows, it usually means intuition is the wrong tool. Human intuition evolved to throw rocks, judge distances across valleys, maybe navigate oceans. It did not evolve to reason about systems where time itself becomes a variable that refuses to behave. At these scales, the universe doesn't feel dramatic. It feels indifferent. The galaxy didn't grow explosively. It didn't announce itself. It simply persisted, quietly feeding from its environment, possibly drawing material along vast dark matter filaments that connect clusters across the cosmic web. If that's true, and evidence increasingly points that way, then galaxies aren't isolated islands at all. They're pressure points in a much larger system, shaped by flows we barely detect. That reframes everything. Instead of galaxies being the main actors, they become symptoms, expressions of deeper structures that stretch across the universe like scaffolding. And once you accept that, the idea of the biggest galaxy starts to feel almost misleading. Size becomes less about mass or brightness and more about how deeply something is embedded in the universe's underlying architecture. Time makes this even stranger. For a structure this large to exist, it must remain stable across billions of years. That means no catastrophic mergers, no environmental collapse, no sudden shutdown of the engine at its core. While continents drifted on Earth and species blinked in and out of existence, this galaxy's influence continued to expand. Light that left one end of it began its journey before the first mammals walked the planet and still hasn't arrived at the other side. And the most unsettling detail is how casually we found it. Not because we expected it, not because theory demanded it, but because wide-field radio surveys happened to catch something that didn't fit. Which raises a quiet but dangerous question. If we found one by accident, how many more are out there? Neil deGrasse Tyson has warned repeatedly that we mistake the limits of our instruments for the limits of reality. The universe does not scale itself to our expectations. It tolerates extremes effortlessly. It produces outliers without apology, and it does not stop doing so just because our models feel complete. By the time you reach this realization, the discovery stops feeling like an achievement and starts feeling like a warning. Because if galaxies can grow this large, persist this long, and reshape space on this scale, then the universe is far more permissive and far less intuitive than we're comfortable admitting. The question is no longer how big this galaxy is. The question is whether big is even the right word anymore. And that's not all. The deeper issue is what kind of universe allows size to keep scaling without an obvious ceiling. Because physics, at least the version we teach, is supposed to be full of ceilings. Speed limits, energy limits, stability limits. And yet here is a galaxy that appears to have ignored several of them at once. To understand why that's disturbing, you have to stop thinking of a galaxy as a collection of stars and start thinking of it as a long-term negotiation between gravity and expansion. Gravity wants everything to fall inward. Expansion wants everything to drift apart. Most galaxies are compromises between those two forces. They grow until feedback kicks in. Star formation heats gas. Supernovae blow material away. Black holes inject energy that prevents further collapse. Growth slows. Equilibrium emerges. Except in this case, equilibrium never really arrived. The black hole at the center didn't simply turn on, feed, and calm down. It stayed active long enough and coherently enough to drive jets that cross distances where the universe itself is stretching space faster than galaxies can drift. That means these jets weren't just strong. They were persistent, stable across epochs, resistant to disruption in a universe that specializes in disruption. And persistence is far harder to explain than power. Power can be brief. A supernova releases more energy in seconds than the sun will in its entire lifetime. Persistence requires structure. It requires conditions to remain aligned over timeframes that dwarf civilizations, planets, and even species. Something had to keep feeding that central engine without interruption, without misalignment, without catastrophic interference. This is where dark matter quietly takes center stage. Galaxies don't form where stars form. They form where dark matter gathers. Dark matter outweighs normal matter by roughly 5-to-1, and it doesn't glow, collide, or dissipate energy the way ordinary matter does. It forms vast halos that act like gravitational scaffolding. Stars, gas, and dust merely decorate that scaffolding. If this galaxy reached such absurd dimensions, it likely didn't do so alone. It may sit at the intersection of multiple dark matter filaments, the cosmic highways that funnel material across the universe. Instead of being a self-contained island, it could be more like a knot in a web, constantly fed from multiple directions for billions of years. That idea is deeply uncomfortable because it reframes what a galaxy is. It stops being a discrete object and starts looking like a process, an ongoing flow of matter shaped by invisible structure on scales larger than anything we can easily visualize. If that's true, then the question, how big can a galaxy get, has no simple answer. Growth doesn't stop when stars run out. It stops when the cosmic environment changes, and in some regions, that change may take an absurdly long time. This also forces a rethink of time. When we say this galaxy is millions of light years across, we're collapsing a time gradient into a single snapshot. Light from the far edge left earlier than light from the near edge. What we're seeing is not one moment, but a stretched-out history layered across space. Parts of this structure may already be evolving differently than others, but we experience them simultaneously because light doesn't care about narrative coherence. That means even our description of the galaxy is a compromise with relativity. The universe doesn't present itself all at once. It leaks information at the speed of light, forcing us to assemble reality from fragments of the past. On small scales, that delay doesn't matter. On cosmic scales, it becomes everything. A structure this large is never fully now. It's always partly memory. And that raises an even stranger possibility. If the jets powering this galaxy were active for long enough, they didn't just shape the galaxy, they shaped intergalactic space itself. Jets inject energy into surrounding gas, preventing it from cooling and collapsing into new stars elsewhere. In effect, a single galaxy can regulate star formation across regions that dwarf entire clusters. That turns influence into something almost territorial. Not in a conscious sense, of course, but in a physical one. This galaxy may have altered the evolutionary paths of countless smaller galaxies nearby simply by existing the way it did for long enough. It didn't conquer them. It didn't collide with them. It starved them by heating the environment they depended on. And here's where human intuition fails again. We tend to think of influence as proximity-based. Close things matter more than distant ones. But on cosmic scales, duration matters more than distance. A weak force applied consistently over billions of years can dominate over stronger forces that act briefly. This galaxy didn't need to be violent. It needed to be patient. Neil deGrasse Tyson often emphasizes that the universe rewards patience far more than intelligence. Stars that burn slowly live longer. Galaxies that grow steadily survive longer. Structures that avoid catastrophic events persist. From that perspective, this galaxy isn't an anomaly. It's a winner under the universe's rules, which makes it even more unsettling. Because the rules that allowed it to win are the same rules that govern everything else. There is nothing exotic here. No new physics has been confirmed. No violations detected. This galaxy appears to be doing something extraordinary while staying entirely within the laws we already accept. That's what makes it dangerous to our understanding. When something breaks your expectations without breaking the rules, it means your expectations were never anchored to reality in the first place. They were anchored to convenience, to the sizes and timescales we're used to dealing with. And once that realization sinks in, a quiet shift happens. The universe stops feeling tuned for us to understand. It starts feeling tuned to not care whether we do. There's another layer to this that's even harder to sit with. If structures like this can exist, then the early universe may have been far more uneven than our simplified models suggest. Small differences in density, alignment, or environment could have snowballed into vast disparities over time. Some regions might naturally produce extreme outliers, while others remain comparatively modest. That introduces a kind of cosmic inequality. Not all galaxies are born into the same universe, even if they share the same laws. Their fates depend on where they land in the cosmic web, how matter flows around them, and whether their central engines ignite at just the right moment and orientation. In other words, history matters, even in a universe governed by equations. And that brings us to a deeply unsettling parallel. If galaxies are shaped by long-term environmental advantage, then intelligence, if it exists elsewhere, would be shaped the same way. Civilizations wouldn't rise uniformly across the cosmos. They would cluster where conditions allowed persistence, energy flow, and stability over vast timescales. Which means absence doesn't necessarily imply rarity. It may simply imply scale mismatch. We look for signals that last decades or centuries. The universe prefers processes that unfold over millions or billions of years. A galaxy like this doesn't scream its existence. It whispers it across eons. And suddenly, the phrase, "it's just too big," stops sounding like awe and starts sounding like unease. Because the more we uncover structures like this, the clearer it becomes that the universe isn't built around neat categories. There is no clean separation between galaxy and environment, between object and process, between now and then. Everything bleeds into everything else given enough time. And time, unlike us, is abundant. However, once you let go of the idea that galaxies are tidy, self-contained objects, another problem creeps in quietly, almost unnoticed. It's the problem of expansion. Not expansion as a buzzword, not the balloon analogy we learn in school, but expansion as an active participant in shaping what can and cannot exist. Because while gravity is busy trying to pull matter together, the universe itself is stretching the space between things. And that stretching is not uniform in how it feels. On small scales, gravity wins easily. At the level of planets, stars, even most galaxies, expansion is negligible. Space stretches, yes, but gravity stitches it back together without effort. That's why galaxies don't slowly dissolve as the universe expands. But when you start talking about structures measured in millions of light years, the balance becomes delicate. This is where the largest galaxy ever discovered becomes deeply unsettling. Its sheer size pushes it into a regime where cosmic expansion should matter. Not dominate, but matter. The fact that it remains coherent at all suggests that its gravitational architecture is not merely strong, but exquisitely timed. It formed early enough, grew fast enough, and stabilized before expansion could tear its growth apart. Neil deGrasse Tyson often explains that the universe has phases. Early on, matter dominated, gravity ruled, structures formed quickly. Later, expansion accelerated, driven by dark energy. Growth slowed. New large-scale structures became harder to assemble. There was effectively a cosmic window for building big things. This galaxy appears to have exploited that window almost perfectly, which immediately raises the question: how many others like it might exist that we simply haven't noticed yet? Because detecting something this large is not as straightforward as it sounds. Large doesn't always mean bright. In fact, the larger and more diffuse a structure becomes, the easier it is to miss against the cosmic background. Our telescopes are excellent at spotting compact, energetic objects. They are much worse at identifying extended, faint structures whose light is spread thin across enormous volumes of space. That means the universe could be hiding its most extreme creations in plain sight, simply because they don't shout loudly enough in any single direction. And this is where human intuition really starts to collapse. We imagine discovery as finding something new that stands out sharply against what we already know. But on cosmic scales, discovery often comes from realizing that something ordinary has been quietly exceeding our assumptions for a very long time. This galaxy wasn't hiding behind a curtain. It was hiding behind our expectations. When astronomers began to piece together its true extent, the discomfort wasn't just about size. It was about continuity. This structure didn't appear to have a clean boundary. Its influence faded gradually, blending into the surrounding cosmic web. That blurring of edges challenges the idea that galaxies have clear borders at all. So where does a galaxy end? Is it where stars stop, where gas thins out, where dark matter density drops below some threshold? Each definition gives a different answer, and for something this large, those answers diverge wildly. Depending on how you define galaxy, its size could shrink by half or double outright. That ambiguity isn't a technical nuisance, it's a philosophical crack. It suggests that some of our most basic categories in cosmology are provisional, useful approximations, not fundamental truths. We label structures to make the universe legible, but the universe doesn't respect those labels. Neil deGrasse Tyson has a habit of reminding audiences that nature does not care about our filing systems. It does not know what a galaxy is. It only knows physics unfolding in time. If matter keeps flowing, if gravity keeps binding, if nothing interrupts the process, then growth continues, regardless of what we call the result. And now consider this. If galaxies can grow to this scale, what does that say about the largest possible structures in the universe? For decades, cosmologists have assumed there is a rough upper limit to coherent structure size. Beyond a certain scale, expansion wins decisively. Matter can't clump fast enough. Structures smear out. The universe becomes smooth again. But discoveries like this force that assumption into uncomfortable territory. They don't outright disprove it, but they push against it hard enough to make us recheck the math, the simulations, the initial conditions. And simulations are where things get especially interesting. When cosmologists model galaxy formation, they rely on initial fluctuations in the early universe, tiny differences in density that grew over time. Most simulations produce galaxies roughly the size we expect. Occasionally, they produce outliers, rare giants, but structures on this scale are uncommon even in virtual universes designed to explore extremes, which suggests one of two things. Either this galaxy formed under exceptionally rare initial conditions, a cosmic lottery win, or our simulations are missing subtle, long-term effects that only reveal themselves at the largest scales. Effects that don't matter for ordinary galaxies, but compound relentlessly over billions of years. That's a humbling thought. It implies that even with supercomputers and sophisticated physics, our models may still be biased toward the familiar, toward galaxies that look like the Milky Way, toward structures that feel manageable. The universe, meanwhile, may be perfectly comfortable creating things that sit far out on the statistical tails. And tails are dangerous places for intuition. There's also a deeper time problem that creeps in here. A structure this large likely assembled over a significant fraction of cosmic history. That means it has persisted through major transitions, the end of the era of intense star formation, the rise of dark energy dominance, the slow cooling of the cosmic environment. Most galaxies don't survive such transitions unchanged. They merge, fragment, shut down, or fade. This one didn't just survive. It continued to assert itself gravitationally across epochs where conditions were becoming less favorable, which suggests resilience on a scale we rarely talk about. Resilience not in the sense of durability against explosions or collisions, but resilience against cosmic indifference, against the slow, relentless dilution imposed by expansion, against the tendency of complexity to decay. Neil deGrasse Tyson often frames the universe as a place where complexity is temporary. Stars burn out, galaxies age, structure is borrowed, not owned. This galaxy complicates that narrative just enough to make us uneasy. It didn't resist decay forever, nothing does, but it delayed it astonishingly well. And that delay matters, because it means the universe can preserve structure far longer than we instinctively expect, given the right conditions, which in turn suggests that the universe's history may be more structured, more varied, and more uneven than our broad-brush models imply. Now zoom out further. If expansion doesn't immediately erase large structures, and if dark matter scaffolding can support growth on these scales, then the distinction between galaxy, cluster, and supercluster starts to blur. These categories are partly historical artifacts, ways we group things as our observational reach expanded. The universe didn't suddenly invent superclusters. We did when our maps got better. This galaxy sits uncomfortably close to that boundary, too big to feel like a galaxy in the traditional sense, too coherent to be dismissed as a loose collection of galaxies. It occupies a gray zone that forces a rethink of cosmic architecture. And that rethink has consequences. If our categories shift, then so do our estimates of mass distribution, gravitational influence, and even the universe's overall geometry. Large structures affect how light bends, how background radiation is distorted, how distances are inferred. A single extreme outlier can bias measurements if we don't account for it properly. So this isn't just an abstract curiosity. It feeds back into how we measure the universe itself. And that leads to an uncomfortable meta-question. How many of our precise measurements depend on assumptions that quietly break down at extreme scales? Neil deGrasse Tyson often warns against confusing precision with accuracy. You can measure something very precisely using the wrong model and never notice the error until you push into unfamiliar territory. Discoveries like this galaxy are exactly that push. They don't overthrow cosmology, they stress test it. And stress tests are where hidden weaknesses reveal themselves. The more astronomers examine this object, the clearer it becomes that it's not just a monster in size but a mirror. It reflects back our habits of thought, our tendency to extrapolate from the familiar, our comfort with averages, our trust in neat boundaries. The universe, once again, refuses to cooperate. And here's the quiet twist that makes this even more unsettling. Cosmic expansion is accelerating. Dark energy is becoming more dominant with time. The era when structures like this could form is already fading into the past. The universe is moving toward a future where new large-scale structures become increasingly rare. Which means this galaxy is not just big, it's early. It formed at just the right moment in cosmic history to exploit conditions that no longer exist. In that sense, it's a fossil of a more permissive universe, a relic from an era when gravity still had enough leverage to build absurd things. And fossils tell stories not just about what existed, but about what is no longer possible. That realization adds a subtle melancholy to the discovery. We're not just observing something extraordinary, we're discovering the limits of what we can ever see. Because once a structure grows beyond a certain scale, observation itself starts to fail in quiet, structural ways. Neil deGrasse Tyson often points out that astronomy is not the study of objects, it's the study of light that happens to reach us, and that distinction matters here more than anywhere else. This galaxy does not announce itself as a single, obvious thing. Its light is stretched thin across space, diluted by distance, redshifted by expansion, and partially erased by the universe's own geometry. In other words, the bigger something becomes, the harder it is to prove it exists at all. This is where our instruments start lying to us, not intentionally, but inevitably. Telescopes are designed to detect contrast, bright things against dark backgrounds, sharp edges, concentrated energy. But a structure that spreads itself over tens of millions of light years doesn't behave like a spotlight. It behaves like fog, and fog is invisible until you're already inside it. So how do you detect something you can't clearly separate from its surroundings? You don't see it directly, you infer it. Astronomers noticed subtle patterns in how smaller galaxies moved, tiny deviations in velocity, unexpected gravitational pulls, light bending just a little more than it should. No single observation screamed giant galaxy. But when the data was stacked over decades, across surveys, across wavelengths, a shape began to emerge. Not a clean shape, a statistical one. And this is where human intuition starts to break again. We're comfortable with objects we can point to, less comfortable with objects that only exist as patterns in data. This galaxy forced astronomers to accept that some of the universe's largest structures are not things you photograph, they are things you reconstruct. Neil deGrasse Tyson has said that the universe often hides its most important truths not in dramatic events, but in deviations so small they're easy to dismiss. This discovery is a perfect example. It wasn't found because it was obvious. It was found because something didn't quite add up. And once you accept that, a disturbing implication follows. If we only notice such structures when they influence smaller, more visible objects, how many could exist that do? A structure that doesn't strongly lens light, that doesn't disturb nearby galaxies enough, that sits just below our detection threshold. Entire cosmic giants could be effectively invisible to us, not because they're far away, but because they're too diffuse to announce themselves. This is not a failure of technology alone. It's a fundamental constraint of observation in an expanding universe. As space expands, light stretches. Surface brightness drops. Beyond a certain distance, even enormous objects fade into statistical noise. The universe doesn't just limit how far we can see, it limits how clearly we can interpret what we see. And that leads to a deeply uncomfortable thought. Our map of the universe may be systematically biased toward things that are compact, energetic, and loud. The universe's quiet giants may be undercounted or missed entirely. Neil deGrasse Tyson often frames this as a cosmic selection effect. We don't see what exists. We see what survives the journey to our detectors, which means the universe we think we know may be a filtered version, shaped as much by physics as by our own perceptual constraints. This galaxy sits right at that edge. Its discovery required not just better instruments, but better patience, longer surveys, wider fields of view, willingness to question whether missing mass and strange motions might be signs of something structural rather than anomalous. And once that door opens, it doesn't close politely, because the same logic applies elsewhere. If galaxies can grow this large, and if some of them are nearly invisible by direct observation, then our estimates of cosmic mass distribution may be incomplete. Dark matter maps rely on how visible matter behaves. If visible matter is embedded in structures we don't fully recognize, then our reconstructions inherit that blind spot. That doesn't mean our cosmology is wrong. It means it may be unfinished in ways that only show up at extremes. This is why Tyson often emphasizes humility in science, not as a moral stance but as a practical necessity. The universe doesn't reward confidence. It rewards curiosity paired with restraint. Now consider the timing of all this. We live in a universe that is becoming harder to observe over time. As expansion accelerates, distant galaxies slip beyond our cosmic horizon. Their light will never reach us. Structures that exist now will eventually be causally disconnected from us forever. Which means we are observing the universe during a temporary window, one where large-scale structure is still partially accessible. This galaxy is not just a discovery, it's a reminder of that window. There was a time when the universe was too young for such structures to exist. There will be a time when the universe is too expanded for us to detect them. We happen to exist in the narrow slice where both formation and observation overlap. That coincidence is easy to overlook, but it matters. Because it suggests that some truths about the universe are time-sensitive. Miss the window and the evidence disappears forever. Not destroyed, just unreachable. Neil deGrasse Tyson often uses this idea to reframe cosmic exploration. We are not explorers moving outward. We are archivists racing against expansion, trying to catalog a universe that is slowly erasing its own history. And the largest galaxy ever discovered feels like a page half burned at the edges. We can still read it, but only barely. Which raises a deeper question. How much of cosmic history has already slipped beyond our reach? Galaxies that formed early and faded, structures that assembled briefly and dissolved, patterns that left no strong gravitational scars. The universe may have gone through architectural phases we will never reconstruct, simply because their evidence diluted too quickly. This galaxy survived long enough to be noticed, others may not have. And that survival tells us something subtle about the universe's priorities. Not everything that forms gets remembered, only what persists leaves a trace. This is a brutal filter. It favors stability over brilliance, endurance over drama, structures that quietly hold together across billions of years. That may explain why the universe appears calmer than we expect. Violent events happen, but they fade. Long-lived structures dominate what we observe. Which makes this galaxy scale even more unsettling. It didn't just form, it endured. And endurance on cosmic scales is rare. As astronomers continue to refine their observations, they're faced with a philosophical fork in the road. Either this galaxy is an extreme outlier, a once-in-a-cosmic-age anomaly, or it's a hint that our census of the universe is incomplete in a systematic way. Both options are uncomfortable. If it's an outlier, we must explain how such improbability occurred without breaking our models. If it's not, we must accept that the universe is more crowded with giants than we thought, giants we've been overlooking. Neil deGrasse Tyson has said that the most dangerous assumption in science is that what you haven't seen doesn't exist. The universe has punished that assumption repeatedly. This discovery may be another warning shot. And here's where the story turns inward. Because as we push deeper into cosmic scales, we're forced to confront the limits not just of technology, but of human cognition. Our brains evolved to understand objects you can walk around, not structures that span millions of light years and reveal themselves only through statistical inference. We are asking minds built for savannas to interpret a universe that operates on scales where intuition fails completely. And yet we keep trying. That persistence, flawed, limited, but relentless, is what makes discoveries like this possible at all. However, what has been discovered seems to be just the tip of the iceberg. What makes this galaxy truly destabilizing isn't just its size or how hard it was to detect. It's the fact that it should not exist at all without something we still don't understand. And that something is dark matter. Neil deGrasse Tyson often says that if you remove dark matter from the universe, galaxies don't just change shape, they fail to form entirely. Gravity alone, acting through visible matter, simply isn't strong enough to assemble structures on this scale before the universe expands them apart. The discovery of a galaxy this large pushes that truth from theory into something almost uncomfortable to look at directly. Because this galaxy is not just sitting in dark matter. It is dominated by it. To understand why that matters, you have to let go of how we normally imagine galaxies. Most people picture them as islands of stars, gas, and dust, glowing spirals floating in space. But that image is misleading. In reality, the stars are a minor component. The visible galaxy is more like foam floating on top of a vast, invisible ocean. Dark matter outweighs ordinary matter by roughly 5 to 1. It does not emit light. It does not absorb light. It barely interacts with anything except through gravity. And yet, it is the scaffolding on which every large cosmic structure is built. This galaxy is so massive that its visible stars alone could never stay bound. They would drift apart. The expansion of the universe would tear them loose long before gravity could organize them into a coherent structure. The only reason they remain connected is because something else is holding them together. And that something cannot be seen. Neil deGrasse Tyson has described dark matter as the universe's invisible architecture. You never see the beams. You only notice them when the building doesn't collapse. This galaxy is an extreme case, a building so large that its invisible beams must be unimaginably vast, which forces a difficult realization. If dark matter halos can grow this large, then our understanding of how dark matter behaves on the largest scales may be incomplete. Standard cosmology predicts that dark matter clumps hierarchically. Small structures form first, then merge into larger ones. Over time, this process builds galaxies, clusters, and superclusters. But the size of this galaxy stretches those expectations. Its dark matter halo appears not just large, but unusually coherent, as if it resisted fragmentation while growing. That raises questions no one was forced to ask before. Does dark matter always behave the same way at every scale? Is it perfectly cold and collisionless, as current models assume? Or could there be subtle interactions that only become visible when structures reach this extreme size? Neil deGrasse Tyson is careful here. He doesn't claim dark matter is misunderstood, but he does emphasize that we only know it through its effects. We infer its presence by watching how visible matter moves. That means every conclusion about dark matter is indirect, layered, and model-dependent. This galaxy presses on those layers. Its rotation curves, how fast stars orbit at different distances, don't taper off the way ordinary matter would predict. The outer regions move as if embedded in a gravitational field far stronger than visible mass allows. That's expected for galaxies, but not at this scale. The implication is unsettling. Dark matter may organize itself into structures that are not just larger versions of smaller halos, but qualitatively different ones. And if that's true, then dark matter isn't just passive scaffolding. It may have its own large-scale behavior, patterns we've barely begun to map. This is where the discovery stops being about one galaxy and starts becoming about the universe's deep rules. Because if dark matter can create and sustain structures this large, it may also influence how galaxies form environments capable of hosting stars, planets, and potentially life. Large halos trap gas more effectively. They regulate star formation. They shape the chemical evolution of galaxies over billions of years. Which means dark matter indirectly influences whether complex structures, including life, ever emerge. Neil deGrasse Tyson often reminds audiences that we are made of atoms forged in stars, and stars are governed by gravity. If gravity behaves differently at extreme scales because of dark matter, then the universe's capacity to generate complexity is tied to something fundamentally unseen. That realization shifts perspective again. This galaxy isn't just a curiosity. It's a test case for whether the universe's invisible components are as simple as we assume. Now consider something even more disturbing. Dark matter does not cool. It does not radiate energy away like gas does. Once it collapses into a halo, it stays diffuse. That means these enormous dark matter structures are ancient. They formed early and persist for billions of years with little internal change. This galaxy's halo may be among the oldest large structures still intact, which means it carries a memory of the universe's early conditions, frozen into its gravitational field. In a sense, dark matter halos are time capsules. They preserve information about how density fluctuations grew in the early universe. The larger and more pristine the halo, the more directly it reflects those primordial conditions. This galaxy may be telling us something about the universe's first moments, not through light, but through gravity. And gravity, unlike light, does not fade with expansion. It stretches infinitely, it accumulates, it binds. Neil deGrasse Tyson has said that gravity is the universe's long memory. Everything else forgets. Radiation redshifts away, heat dissipates, motion decays, but gravity remembers. This galaxy is a memory that refuses to be erased, which leads to a deeply unsettling possibility. If dark matter structures can grow this large and remain stable, then some of the universe's most important features may be entirely invisible to us except through indirect effects. There could be vast regions where dark matter dominates so completely that visible galaxies are mere tracers, faint sparks embedded in something far larger. We may be living in a universe where the most important structures are the ones we cannot see. That idea collides head-on with how humans intuitively understand reality. We trust light, we trust images, we trust what can be pointed at. Dark matter defies all of that. It forces us to accept a universe where the dominant component is fundamentally unobservable. Neil deGrasse Tyson often frames this as a humbling moment in scientific history. Just as we once believed Earth was the center of everything, we now must accept that visible matter, including us, is not the main event. This galaxy reinforces that truth brutally. Its stars are decoration, its dark matter is the structure. And here's where the story quietly becomes philosophical. If the universe is primarily shaped by something we cannot see, then our sense of cosmic understanding will always be incomplete. Not because we lack intelligence, but because reality itself withholds direct access to its foundations. This doesn't mean science fails. It means science operates under constraints. We measure, we infer, we test, but some things remain one step removed from experience. Neil deGrasse Tyson has argued that this distance is not a flaw, it's a feature of a universe that demands humility. We don't get handed truth, we earn approximations. This galaxy pushes that lesson to an extreme. Because even as we celebrate its discovery, we must admit that we didn't see it in the way we see a star or a planet. We reconstructed it from gravitational fingerprints, from what it does to others. That's how dark matter always announces itself. The discovery feels quite unsettling, right? However, if this feels crazy for you, wait until you hear about the very idea of cosmic uniformity. The idea that the universe looks roughly the same everywhere is so deeply baked into modern cosmology that most people never realize it's an assumption at all. It's called the cosmological principle, the belief that, on the largest scales, the universe is homogeneous and isotropic. No special places, no preferred directions, no regions that fundamentally break the rules. Neil deGrasse Tyson often describes this principle as the quiet foundation under almost everything we calculate about the cosmos. Without it, our equations become fragile. Our predictions lose their footing. The universe stops being something we can generalize about. And that's exactly why this galaxy is so troubling. Because when you zoom out far enough, galaxies aren't supposed to stand out like this. You can have clusters, you can have filaments, you can have voids, but they're expected to average out. Large structures should be balanced by equally large emptiness elsewhere. No single object should dominate its cosmic neighborhood to this degree. Yet here it is. A galaxy so massive that it stretches the meaning of largest without fitting neatly into the expected hierarchy of cosmic structure. This is where the conversation quietly shifts from discovery to discomfort. Because if one galaxy can grow this large without violating known physics outright, then the universe may not be as uniform as we assume, only uniform enough that the cracks don't usually show. Neil deGrasse Tyson has said that cosmology often advances not by finding new things, but by finding exceptions to things we thought were universal. This galaxy is exactly that kind of exception. On paper, the universe's large-scale structure emerges from tiny fluctuations in the early cosmos, minute variations in density, amplified over billions of years by gravity. These fluctuations are measured in the cosmic microwave background, the afterglow of the Big Bang, and those measurements are astonishingly smooth, almost boringly so, which is why structures like this feel wrong. To get something this large, you either need an unusually dense initial region, or you need growth mechanisms that outperform the average cosmic expansion. Neither option is impossible, but both challenge the idea that average truly governs everything. And here's where things become subtly dangerous for our models. If the universe allows rare but extreme outliers, then our statistical descriptions may hide important physics. We may be mistaking rarity for impossibility simply because we haven't looked long enough. Neil deGrasse Tyson often warns against confusing "we haven't seen it" with "it can't happen." The history of astronomy is full of that mistake. Black holes were once theoretical curiosities. Exoplanets were dismissed as unlikely. Even galaxies outside the Milky Way were once controversial. This galaxy now joins that lineage, not as a new category of object, but as a new scale of possibility. And scale matters, because cosmology doesn't just ask what exists, it asks how the universe behaves as a whole. If extreme structures exist, they influence how matter flows, how light bends, how expansion proceeds locally. They become gravitational landmarks in an otherwise smooth cosmic terrain. Which leads to a deeply unsettling question. What if the universe is only statistically uniform, not physically uniform? That sounds like wordplay, but it's not. Statistical uniformity means that if you average over enormous volumes, things balance out. Physical uniformity would mean no region ever deviates too far from expectation. The first allows monsters, the second forbids them. This galaxy suggests the universe favors the first. And once you accept that, the implications cascade. Because gravitational monsters don't just sit quietly, they distort spacetime around them. They lens background galaxies. They redirect flows of gas and dark matter across tens of millions of light years. They alter the local expansion rate in subtle but measurable ways. In other words, the universe may not expand the same way everywhere. Neil deGrasse Tyson has emphasized that cosmic expansion is not like an explosion with debris flying outward uniformly. It's spacetime itself stretching. But that stretching can be locally resisted by gravity. In dense regions, expansion slows. In underdense regions, it accelerates. Now imagine a structure this massive. It doesn't just resist expansion, it competes with it. This galaxy's gravitational influence could extend far beyond its visible boundary, subtly warping the trajectories of nearby galaxies and altering the growth of structure around it. In effect, it becomes a regional anomaly in the universe's otherwise smooth unfolding. Which means that if you lived near it, truly near it on cosmic scales, your measurements of the universe might not match those made elsewhere. This is where cosmology brushes up against something almost philosophical. We assume our cosmic measurements are representative, that the universe we infer from Earth is the universe as a whole, but that assumption depends on us not living in an unusual region. Neil deGrasse Tyson has joked that every civilization thinks it occupies a special place until science tells it otherwise. But this galaxy raises the inverse concern. What if some regions really are special? Not chosen, not designed, just statistically rare. If that's the case, then cosmic history becomes less like a smooth narrative and more like a landscape with peaks and valleys, most of it flat, but punctuated by extremes that matter disproportionately. This forces cosmologists to revisit how they interpret survey. When we map the universe, we rely on sampling. We can't see everything. We extrapolate from what we observe. But if rare giants exist, then small samples may mislead us. Our cosmic census could be incomplete in the most consequential way possible, missing the outliers that define the limits of structure. Neil deGrasse Tyson often reminds people that science is not about certainty. It's about confidence levels. And confidence depends on knowing how likely you are to be fooled by rare events. This galaxy is a reminder that the universe can fool us politely for a long time. And then suddenly it doesn't. There's another layer to this problem that's even more unsettling. Large structures like this don't just challenge uniformity in space, they challenge uniformity in time. Because to grow this large, the galaxy must have had a long, uninterrupted growth history. That implies a region of the universe that remained stable gravitationally and dynamically for billions of years without being disrupted by collisions, mergers, or violent feedback. That kind of cosmic calm is not guaranteed. The early universe was chaotic. Galaxies collided frequently. Star formation was intense. Black holes were active. Energy was being injected everywhere. For a structure to grow steadily through that era suggests an environment unusually favorable to long-term accumulation. In other words, this galaxy may not just be large. It may be ancient in a way that exceeds our expectations. Neil deGrasse Tyson has spoken about the difference between age and history. Two objects can be the same age but have very different pasts. This galaxy's past may be unusually quiet, allowing it to become something the universe rarely permits. Which raises a question that feels almost uncomfortable to ask. If such regions exist, what else might have happened there? Long-term stability is a prerequisite not just for large galaxies, but for complex processes, including the slow evolution of stars, planetary systems, and potentially life. While there's no evidence this galaxy hosts life-bearing worlds, its existence forces us to reconsider how cosmic environments influence possibility. The universe may not be equally friendly to complexity everywhere. Some regions may be too violent, others too sparse, and a few, very few, may sit in a sweet spot for absurd lengths of time. This galaxy could be a marker of such a region. Neil deGrasse Tyson often cautions against anthropocentrism, the mistake of assuming the universe is structured with us in mind, but recognizing that some regions are more conducive to complexity than others doesn't recenter humanity. It decenters us further. It suggests that even the universe itself is uneven in its generosity. And now we reach a quiet but profound shift. This discovery doesn't just challenge how galaxies form, it challenges how we define typical. If typical excludes the extremes, then it may miss the most informative cases. The boundaries teach us more than the averages. This galaxy lives at the boundary. And boundaries are where models break or evolve. Having this in mind, does the idea of limits really work here? At some point, every scientific model quietly relies on an unspoken belief that there is a limit. A fastest speed, a smallest length, a largest structure. These limits give physics its shape. They're what stop the universe from becoming an anything-goes nightmare where prediction collapses. Neil deGrasse Tyson has often explained that the speed of light isn't just a number. It's a boundary that turns chaos into structure. Without limits, science stops being science and becomes storytelling. And that's exactly why this galaxy feels dangerous. Because once you accept that something can grow this large, a natural question follows, not dramatically, not loudly, but relentlessly. What stops the next one from being even bigger? Until recently, cosmologists believed they had an answer. Large-scale structure, according to standard cosmology, emerges from a balance between gravity and expansion. Gravity pulls matter together. Cosmic expansion pulls it apart. Over time, these forces reach a kind of statistical truce. Structures grow, but only up to a point. Beyond that, expansion wins. That's why galaxies cluster. That's why clusters form superclusters. And that's why, eventually, structure should stop. The universe, we thought, had already drawn the line. But this galaxy sits uncomfortably close to that line, close enough that it forces us to ask whether the line is real, or whether it was just a convenience born of limited observation. Neil deGrasse Tyson has said that the most unsettling discoveries aren't the ones that break laws outright, but the ones that obey the laws too well while still violating our expectations. This galaxy does exactly that. It doesn't require new physics. It doesn't contradict relativity. It doesn't overthrow dark matter or dark energy. It simply exists. And that's worse. Because if the universe permits structures of this scale under known physics, then the constraints we thought were fundamental may only be probabilistic. The universe may not enforce strict ceilings, only tendencies. In other words, unlikely may not mean impossible. That distinction sounds small. It is. In a universe 13.8 billion years old, with hundreds of billions of galaxies, even extremely rare events eventually happen. If you wait long enough, improbability becomes inevitability. This galaxy may be the proof, which leads to a deeply uncomfortable realization. Our models may be averages, not rules. Cosmology relies heavily on statistical descriptions. We talk about mean densities, average expansion rates, typical galaxy sizes. These concepts work beautifully when deviations are small. But when deviations grow large, averages stop telling the whole story. Neil deGrasse Tyson often reminds people that statistics can hide monsters. If you average the heights of humans, you'll never predict someone 7 feet tall. The average doesn't forbid giants, it just ignores them. Now imagine applying that logic to the universe. If our cosmological models are built on averages, then extreme structures are not violations, they're blind spots. The universe isn't breaking rules, it's exploiting the space between them. And that raises a disturbing possibility. There may be no absolute upper limit to cosmic structure size, only limits imposed by time, chance, and environment. If that's true, then the universe's largest structures aren't defined by physics alone, but by history, by which regions got lucky early, by where matter happened to pile up just enough, just soon enough, to snowball faster than expansion could tear it apart. This galaxy may be a survivor of that early advantage. Neil deGrasse Tyson has spoken about cosmic evolution as a kind of natural selection, not of life, but of structure. Regions with slightly higher density grow faster. Faster growth attracts more matter. More matter deepens gravity, and so the feedback loop begins. Most regions never escape mediocrity. A few do. This galaxy appears to be one of those few. And if that's the case, then the universe is not just expanding, it's remembering its earliest imbalances. Tiny differences from the dawn of time may echo forward for billions of years, producing structures that feel almost intentional, even though they are not. Which leads to a question that feels almost taboo in physics. Is there a largest possible galaxy at all? Or is the concept itself misguided? Neil deGrasse Tyson has cautioned against assuming nature respects the categories we invent. We name things, planets, stars, galaxies, and then expect nature to obey those definitions. But nature doesn't care what we call things. A galaxy is not a natural kind, it's a convenience. And when galaxies merge, accrete, and blur into clusters, the boundaries become semantic rather than physical. At extreme scales, the distinction between largest galaxy and small cluster becomes fuzzy. This galaxy sits precisely in that gray zone. It's large enough to challenge the definition of a galaxy, yet cohesive enough to resist being reclassified as something else. It occupies a liminal space, structurally stable, gravitationally unified, but conceptually awkward. That awkwardness matters, because it suggests that our cosmic taxonomy may be oversimplified. The universe may host structures that don't fit neatly into our bins, not because they are new, but because our bins are too rigid. Neil deGrasse Tyson has often pointed out that astronomy progresses by embarrassment, by moments when observations force scientists to admit that their categories were provisional all along. This galaxy is embarrassing in exactly that way. It forces cosmologists to ask whether they've underestimated the universe's capacity for scale. And once you accept that possibility, the implications widen rapidly. If galaxies can grow larger than expected, then the distribution of matter on cosmic scales may be more uneven than predicted. That unevenness would affect how light travels across the universe. It would influence gravitational lensing measurements. It could subtly bias estimates of dark matter density and dark energy strength. In other words, rare giants don't just exist quietly, they contaminate measurements. Neil deGrasse Tyson has explained that cosmology is a game of precision. Tiny errors compound over vast distances. A few unaccounted for anomalies can ripple through entire models, which means that discovering one such galaxy isn't just an oddity, it's a calibration problem. Are our measurements skewed because we didn't know to look for things like this? And more unsettling still, what if this isn't the only one? Astronomy is limited by where we look and how deeply we look. Surveys have finite resolution. Detection thresholds filter out faint or diffuse structures. It's entirely possible that similarly massive galaxies exist, unnoticed because they don't shine brightly enough or sit in crowded regions where their boundaries are hard to distinguish. Neil deGrasse Tyson often says that the universe doesn't hide things maliciously. It hides them by being vast. What we haven't seen may dwarf what we have. If this galaxy exists within our observational reach, then others may exist beyond it. And if others exist, then the true upper scale of structure may be far beyond what current models anticipate. This leads to a quiet but radical shift in perspective. Instead of asking, how did this galaxy form? We may need to ask, why don't more galaxies look like this? The answer may lie not in physics, but in probability. Most regions never get the right initial conditions. Most structures are disrupted by mergers, feedback, or expansion before they can grow to extreme scales. This galaxy may simply be the statistical tail, the one that beat the odds. But statistical tails matter. They tell you about the shape of the distribution. They reveal whether there are hard cutoffs or long, dangerous slopes where extremes can grow without bound. This galaxy suggests the slope may be longer than we thought. Neil deGrasse Tyson has often said that the universe is under no obligation to be tidy. If nature prefers messiness with rare order, then that's what we get, even if it complicates our equations. Which brings us to a subtle but profound conclusion. The biggest threat this galaxy poses to human understanding isn't that it's too large. It's that it hints the universe may not have a maximum scale for complexity, only a maximum patience for our assumptions. And patience, in a universe measured in billions of years, is a resource we tend to underestimate. In the next part, this idea collides with something even deeper: how such extreme structures affect our understanding of dark matter and dark energy, the invisible scaffolding that shapes everything we see. Because if the universe allows giants like this, then the unseen forces guiding growth may be doing far more than we realized. At the deepest level, this galaxy forces us to confront something we rarely like to admit in cosmology. Most of what shapes the universe is invisible. Neil deGrasse Tyson often reminds people that everything we can see, stars, gas, dust, galaxies, makes up only a tiny fraction of reality. Roughly 5% of the universe is ordinary matter. The rest is dark matter and dark energy, not metaphors, not placeholders, real components of the universe that dominate its behavior while refusing to show themselves directly. And when something breaks our expectations at galactic scale, the first suspect is always the unseen. Because visible matter alone cannot build a structure like this. Stars are not heavy enough, gas is not dense enough, radiation pressure fights against collapse. Left to ordinary matter, galaxies stall out early, they fragment, they disperse. They never reach these extremes. What allows growth to continue is dark matter. Dark matter doesn't shine. It doesn't absorb light. It barely interacts with normal matter at all. But it has mass, and mass means gravity, and gravity means structure. Every galaxy we know sits inside a dark matter halo, an invisible gravitational skeleton far larger than the luminous galaxy itself. The stars we see are just decorations hung on a much larger, darker framework. For most galaxies, those halos have a predictable size range, large enough to bind stars, small enough to remain stable. Cosmological simulations reproduce these halos with impressive accuracy, until you ask them to produce this. Because for a galaxy to grow to this scale, its dark matter halo would need to be enormous, far more massive than what standard models predict for a single coherent system. Neil deGrasse Tyson has explained that dark matter halos aren't supposed to grow indefinitely. They form early, merge hierarchically, and eventually reach an equilibrium where further growth slows. Expansion of the universe stretches space itself, reducing the efficiency of gravity at very large scales. In theory, that should cap halo size. Yet this galaxy appears to sit inside a halo that either ignored that cap or formed under conditions we haven't fully accounted for. This is where the discomfort deepens. Because dark matter isn't just responsible for holding galaxies together. It shapes how they form, how they rotate, how they merge, and how they survive. If a halo this large exists, it suggests that dark matter may clump more efficiently or more unevenly than our simulations allow. That doesn't mean dark matter behaves differently at a fundamental level. It may mean we misunderstand its distribution. Cosmological simulations rely on initial conditions drawn from the early universe, tiny fluctuations in density left over from the Big Bang. These fluctuations seed structure formation. Over billions of years, gravity amplifies them. Most simulations assume these fluctuations follow a smooth statistical pattern, but statistics always have outliers. This galaxy may be the result of a rare fluctuation amplified relentlessly over cosmic time. A region that started just slightly denser than average, but early enough and isolated enough to snowball without interruption. Neil deGrasse Tyson has pointed out that the universe is a master of amplification. Small differences don't stay small, they cascade. What begins as a whisper can become a roar if nothing intervenes. Dark matter, being collisionless and patient, is particularly good at this. Once a halo starts growing faster than its surroundings, it attracts more matter, deepens its gravitational well, and becomes harder to disrupt. Other structures merge into it rather than tearing it apart. Growth feeds growth. But there's another invisible player here, one that complicates the story further. Dark energy. Dark energy is not a force in the traditional sense. It's a property of space itself, a tendency for space to expand faster over time. On the largest scales, dark energy dominates gravity, driving galaxies apart and suppressing the formation of new large structures. Neil deGrasse Tyson often describes dark energy as the universe's long-term agenda. Gravity builds things locally. Dark energy decides the ultimate fate of everything. And according to standard cosmology, dark energy should make the formation of ultra-large structures increasingly unlikely as the universe ages, which makes the existence of this galaxy particularly awkward. If dark energy has been accelerating expansion for billions of years, then this structure either formed earlier than expected, before dark energy fully asserted itself, or it continued growing in defiance of that expansion. Neither option is comfortable. If it formed early, then massive halos can arise faster than simulations predict. That would imply that dark matter collapsed more efficiently in the young universe than we thought. If it grew late, then dark energy may not suppress structure formation as uniformly as models assume. Its influence may vary with environment, scale, or cosmic history. Neil deGrasse Tyson has emphasized that dark energy is still one of the biggest unknowns in physics. We can measure its effects, but we don't know its nature. We don't know whether it's constant or evolving. We don't know whether it interacts subtly with matter or geometry. A structure like this galaxy presses directly on those uncertainties. Because if dark energy behaves differently in regions of extreme mass concentration, then the universe's large-scale evolution becomes more complex than the clean picture we teach. Instead of a uniform cosmic expansion with local islands of gravity, we may have a patchwork universe, where some regions resist expansion longer, allowing giants to form while others thin out more quickly. That idea isn't speculative fantasy. It emerges naturally from general relativity applied to inhomogeneous matter distributions, but it's mathematically hard and observationally brutal. Neil deGrasse Tyson has said that the hardest truths in cosmology aren't hidden. They're smeared across scales so large that testing them takes generations. This galaxy may be one such truth. Its mere existence hints that our understanding of the balance between dark matter and dark energy may be incomplete, not wrong, but simplified. And simplifications break first at the extremes. There's also the issue of internal dynamics. Galaxies of this size shouldn't be stable for long. Tidal forces, mergers, and internal feedback from star formation typically disrupt coherence. At some point, a structure this massive should fragment into a cluster. Yet this one remains organized. That implies its dark matter halo isn't just massive, it's dynamically calm, cold, smooth, free of violent disturbances that would tear it apart. Neil deGrasse Tyson often notes that stability is rarer than violence in the universe. Things tend to collide, merge, and disrupt. Long-lived coherence is precious. For a galaxy this large to persist, it must have avoided major mergers for billions of years, an astonishing feat in a crowded cosmic environment. That suggests it formed in a relatively isolated region, where growth was fed gently rather than violently. A cosmic backwater where time, not chaos, did the work. Which raises another unsettling thought. Our picture of the universe is biased toward busy regions, clusters, filaments, bright structures. We focus on where action is obvious, but quiet regions may hide the most extreme outcomes simply because nothing interrupts them. Neil deGrasse Tyson has warned that selection bias is one of the most dangerous traps in science. We tend to study what's loud, bright, and dramatic, not what's subtle and patient. This galaxy may be the product of patience, a slow accumulation of matter, guided by invisible forces, untouched by disruption, allowed to grow beyond expectations while no one was looking. If that's true, then similar structures could exist elsewhere, not because the universe favors giants, but because it occasionally tolerates them. And tolerance is enough. At this point, the story stops being about one galaxy. It becomes about how confident we really are in the boundaries we draw around cosmic behavior. If dark matter halos can grow larger than predicted, if dark energy's suppressive role is an absolute, if quiet regions can incubate extremes, then the universe's capacity for scale may exceed our current imagination. Neil deGrasse Tyson often says that the universe doesn't lie to us, but it also doesn't explain itself unless we ask the right questions. This galaxy is forcing new questions. Not dramatic ones about aliens or doom, but structural ones about the universe's architecture. How rigid are the limits we believe in? How universal are the averages we trust? And how many outliers does it take before the distribution itself needs rethinking? In the next part, this tension pushes us into even more dangerous territory, because once scale breaks expectations, it doesn't stop at matter. It reaches into time itself. Because structures this large don't just occupy space, they encode history. And the history implied by this galaxy stretches uncomfortably close to the beginning of everything. When a structure reaches this scale, it stops being just an object in space and starts acting like a record of time. Neil deGrasse Tyson often points out that astronomy is the only science where looking outward is also looking backward. Light doesn't arrive instantly. It carries history with it. Every photon that reaches our telescopes is evidence of a past state of the universe, frozen mid-journey. And for something this large to exist, its history must be long, uninterrupted, and improbably stable. This galaxy is not young. It could not be. Size like this cannot be rushed. Even under ideal conditions, gravity needs billions of years to gather matter across such distances. That means the processes that built this structure began when the universe itself was much younger, denser, and more chaotic than it is now. That's where the discomfort deepens. Because the early universe was not friendly to order. Shortly after the Big Bang, matter was hot, energetic, and nearly uniform. Tiny fluctuations existed, but they were small differences of one part in 100,000. Those differences are what eventually grew into galaxies and clusters, but early on, everything was competing against everything else. Radiation pressure pushed matter apart. Expansion stretched space faster than gravity could pull things together. Structure formation was a slow negotiation between opposing forces. Neil deGrasse Tyson explains that the universe only became truly good at making large structures after it cooled and expanded enough for gravity to dominate locally. Before that, matter struggled to clump. which means that for this galaxy's ancestors to begin forming early enough, they had to sit in a region where conditions were just right, not too turbulent, not too sparse, not too crowded. That alone makes it rare. But rarity isn't the real problem. The real problem is continuity. Most galaxies don't enjoy a peaceful history. Over billions of years, they collide, merge, cannibalize neighbors, and get torn apart by tidal forces. These events are not gentle. They scramble orbits, heat gas, trigger starbursts, and reshape structure. They also erase clean growth histories. This galaxy appears to have avoided that fate. Its scale implies not just early formation, but sustained growth without catastrophic interruption. That suggests a cosmic environment where mergers happened, but in a controlled way, feeding mass without destroying coherence. Neil deGrasse Tyson often emphasizes that the universe is not optimized for stability. Stability emerges only under narrow conditions. Most systems fall apart long before they reach extremes. So when something reaches an extreme and stays there, it means the universe allowed it to. That allowance stretches our understanding of cosmic timelines, because it implies that some regions of the universe experienced a very different evolutionary path than the average one we model. Standard cosmology relies heavily on averages: average density, average expansion rate, average merger frequency. These averages work remarkably well until you encounter an outlier that refuses to behave. This galaxy is not just an outlier in size. It's an outlier in patience. Its existence suggests that the universe can preserve large-scale coherence far longer than we assumed. That gravitational structures, once established early and shielded from chaos, can persist and grow across most of cosmic history. That forces a reevaluation of something subtle but important: how quickly the universe forgets its past. We often assume that early conditions get washed out by later processes, that initial asymmetries blur, that the universe becomes statistically uniform at large scales. But this galaxy suggests that some early advantages may never fully disappear, that the universe remembers more than we think, encoded in structures too large to erase. Neil deGrasse Tyson has said that cosmology is, in many ways, the study of memory: how long information persists, how long cause and effect remain linked. This galaxy may be a memory that survived nearly the entire age of the universe. And that leads to a more unsettling implication. If the universe can preserve structures this large and this old, then our assumption that the universe trends toward smoothness may be incomplete. Instead of inevitable uniformity, the universe may retain long-lived scars, regions where early conditions amplified rather than averaged out. Those scars wouldn't be obvious everywhere. They'd be rare, isolated, easy to miss, until one shows up and refuses to fit. This also complicates how we interpret cosmic timelines. We often divide the universe into eras: radiation-dominated, matter-dominated, dark energy-dominated. These eras describe the dominant force shaping expansion. But local physics doesn't always obey global dominance. Neil deGrasse Tyson frequently reminds audiences that gravity is local, dark energy is global. They coexist, but they don't cancel each other neatly. In dense regions, gravity can overpower expansion for a very long time. That means some structures may continue evolving as if the universe were younger than it actually is. This galaxy could be one of those regions, a pocket of space that effectively lived in a different cosmic era longer than the rest of the universe. That idea is deeply unsettling, because it implies that the age of the universe is not experienced uniformly. Globally, the universe may be accelerating toward isolation and emptiness. Locally, some regions may still be building, growing, and organizing as if expansion hadn't yet won. That challenges the way we narrate cosmic history. Instead of a clean progression from order to dispersion, the universe may be a patchwork of timelines, some regions aging faster, others slower, some freezing early, others staying dynamic far longer. Neil deGrasse Tyson has cautioned against treating cosmology as a single story with one clock. The universe doesn't synchronize itself for our convenience. This galaxy may be evidence of that lack of synchronization. It may represent a region where time, as measured by structure formation, ran differently. And if that's true, then our models of galaxy evolution may be missing entire classes of histories, not because they're impossible, but because they're rare and long-lived. This also reframes how we think about observation. We are seeing this galaxy as it was when its light left it. Depending on its distance, that could be billions of years ago. The structure we observe may no longer exist in the same form, or it may have grown even larger. Neil deGrasse Tyson often points out that astronomy forces humility. We never see things as they are, only as they were. Which means that this galaxy's true story may be even more extreme than what we're witnessing. It could represent a phase of growth that peaked and collapsed later, or it could represent a structure still expanding today, quietly defying the universe's overall trend toward separation. Either possibility stretches our understanding of cosmic time. If it collapsed, then even the largest structures are temporary, fragile on long enough timescales. If it persists, then the universe's ability to sustain order may be greater than we believed. Neither option is comforting, because both undermine the idea that cosmic evolution is simple, predictable, or monotonic. Neil deGrasse Tyson has said that the most dangerous words in science are, "We understand this now." The universe has a habit of waiting until we're confident before introducing a counterexample. This galaxy feels like such a counterexample. It doesn't scream anomaly, it whispers complexity. It suggests that the universe's story is not a smooth arc, but a tangled weave of local exceptions layered over global rules. And once you accept that, another question becomes unavoidable. If the universe can build structures this vast, this old, and this stable, what does that say about the ultimate limits of structure itself? Is there a maximum scale for organization, or are we simply discovering the first examples that approach it? That question pushes us beyond galaxies, beyond clusters, beyond filaments, into the question of whether the universe itself has a preferred scale at all. In the next part, this tension reaches its breaking point. Because once size and time both refuse to behave, we're forced to confront a possibility that Neil deGrasse Tyson has hinted at repeatedly. That human intuition may not just be insufficient for understanding the universe, but fundamentally misaligned with how reality is organized. At some point, the scale stops being impressive and starts being destabilizing. Neil deGrasse Tyson often says that the universe doesn't just challenge our technology, it challenges the way our brains are wired to think. We evolved to understand predators, distances you can walk, timescales you can live through. We did not evolve to understand structures that stretch across hundreds of millions of light years and persist for most of cosmic history. And yet here we are, staring at one. This galaxy doesn't just stretch space, it stretches meaning. Because once something grows this large, it begins to blur categories we rely on to make sense of the cosmos. Is it a galaxy, a protocluster, a fragment of something even larger? Our labels start to fail, and when labels fail, assumptions follow. For decades, cosmology rested on a quiet belief that while the universe is enormous, it is statistically well-behaved at large scales. That beyond a certain size, matter smooths out, that no single structure should dominate the cosmic landscape. This belief isn't philosophical, it's mathematical. It's built into the cosmological principle, the assumption that the universe is homogeneous and isotropic when viewed on sufficiently large scales. In plain terms, no matter where you are and no matter which direction you look, the universe should look roughly the same, once you zoom out far enough. This galaxy tests that assumption, not by breaking it outright, but by leaning on it hard enough to make it creak. Neil deGrasse Tyson has explained that the cosmological principle isn't something we proved. It's something we inferred because it worked. It simplified equations. It matched observations. It allowed us to build a coherent model of cosmic evolution. But models are only as strong as their weakest outliers. And this structure is an outlier with mass. If galaxies can grow this large without violating known physics, then the universe's smoothness scale may be larger than we thought. And if that scale keeps increasing as we discover more distant structures, then the idea of a neat boundary between order and uniformity starts to dissolve. That has consequences far beyond galaxy catalogs. Because cosmology doesn't just describe where things are, it tells us how the universe behaves as a whole. If matter clumps more strongly or more persistently than expected, then our measurements of dark matter, dark energy, and expansion itself may be subtly biased. Not wrong, but incomplete. Neil deGrasse Tyson often emphasizes that precision cosmology depends on knowing what you can safely average over. If the universe contains rare but massive exceptions, then averages may hide important truths. This galaxy might not overturn cosmology, but it may force it to grow up. And that brings us to the most uncomfortable idea of all. Human understanding of the universe didn't fail because we lacked data. It failed because we assumed the universe cared about being understandable. It doesn't. The universe doesn't owe us intuition-friendly behavior. It doesn't owe us symmetry, simplicity, or closure. It only owes us consistency, and even that consistency may operate on scales that feel alien to us. Neil deGrasse Tyson has said that one of science's hardest lessons is learning when to abandon comfort. The moment something feels too strange to be true is often the moment it's closest to being real. This galaxy exists at that edge. It doesn't fit the story we tell about cosmic evolution as a clean progression from chaos to structure to dispersion. Instead, it suggests overlapping narratives, some regions still building while others decay, some memories preserved while others are erased. It suggests that the universe is not converging toward simplicity. It's diverging into complexity. And that realization reframes everything. If structures can persist this long and grow this large, then the future of the universe may not be a uniform fade into darkness. It may be a patchwork islands of structure separated by expanding voids, each with its own history, tempo, and fate. Neil deGrasse Tyson has often described the far future as lonely, galaxies drifting apart, stars burning out, energy thinning. That vision may still be correct globally. But locally, the universe may remain busy far longer than we imagine. And if that's true, then intelligence, wherever it arises, may experience very different cosmic futures depending on where it lives. Some civilizations may watch their skies empty early. Others may inhabit regions rich with structure long after expansion isolates most of the universe. That idea quietly breaks one of our deepest assumptions, that cosmic destiny is shared. It may not be. The universe may offer radically different endings to different regions, not by choice, but by initial conditions amplified over time. This galaxy could be a preview of that divergence, a place where gravity won longer, where structure resisted erasure, where time accumulated instead of washing clean. Neil deGrasse Tyson often reminds us that we are temporary observers. We see a snapshot, not a story arc. And every time we mistake the snapshot for the whole truth, the universe corrects us. This galaxy is such a correction. It tells us that our maps are provisional, our categories fragile, our confidence borrowed. And yet this is not a cause for despair. It's a reminder of why astronomy matters. Because even when understanding breaks, curiosity doesn't. We are still capable of asking questions large enough to meet the universe where it actually is, not where we wish it were. We are still capable of revising our stories when reality refuses to cooperate. Neil deGrasse Tyson has said that the greatest privilege of science is being allowed to be wrong, as long as you're willing to learn from it. This discovery invites exactly that. Not panic, not all alone, but humility. The kind that recognizes that human understanding is not the measure of reality, only its shadow. The biggest galaxy we've discovered doesn't just break human understanding because it's too large. It breaks it because it reveals something we rarely admit. The universe was never built to fit inside our heads. We are visitors here, brief ones, lucky ones. And every time the cosmos reveals a structure this vast, it reminds us that understanding isn't about conquering the universe with explanations. It's about learning how small we are, without losing the courage to keep looking anyway.